Okay, I hope you can see my screen.
Yeah, it's visible.
Perfect. Again, welcome everyone to this second session. Today, I will be discussing about Qiskit foundations. So basically, I'll be discussing about what KitKit is, what Qiskit is, what are the different functionalities it offers, and how one can get started in it. Throughout the session, I will be assuming that some of you, I will be assuming that you already are familiar with uh, very basic of quantum mechanics, although I'll be going through that again, but some familiarity with quantum mechanics is assumed. Nonetheless, let's get started. So, since we are exploring quantum computing, why not just ask why we require quantum computing? Uh, Previously, last yesterday, KG did a fantastic job in explaining why quantum computing is the need of the future. So let me just start with a story. So the initial idea behind the quantum computer was that people wanted to simulate the nature. Basically, people wanted to simulate how would the atoms will behave, how will the molecules will behave. And in order to do that, they previously used to use classical computers in 1970s and 1960s. But then, due to the limitations of computational power of classical computers that they had, they could not simulate any atoms beyond hydrogen, beyond helium atom, because then the complexity was just exponentially increasing. So in 70s and 80s, the famous physicist Richard Feynman actually proposed the idea of using quantum theory to simulate the nature itself, because nature inherently is quantum. So he suggested that why not simulate the nature using the quantum properties of nature itself, instead of using the classical. So this quantum properties of so basically utilization of this quantum properties of nature is what we call the quantum computing. Uh, so yeah, again, why are we interested in quantum computers? So we are interested in quantum computing mainly for the nature simulation, search and optimization, and processing data with structure. So for example, for nature simulation, we want to see how a particular molecule behaves under various conditions. This we want to see to understand the dynamics of the molecular that will help in creating better materials, better drugs, better and lighter, and let's say materials which are better alternative to plastic and everything. So obviously that is one thing. Second thing is search and optimization. Obviously optimization is a need of an hour, because optimization is applied everywhere, from your parcel delivery to your flight scheduling to everything that you can think of. So yeah, these are the some motivation to go into the quantum computers. And now, as KG mentioned yesterday, so quantum computers will not replace your classical computers, they will just complement your classical computers. And the reason for that is that there are certain problems that can be solved only by using quantum computers. For example, secure communication, quantum key distribution, or and as such. So there you rely entirely on quantum computers. However, there are certain class of the problems where your classical computers are good enough, so you don't need to go into the realm of quantum, and it's just better to keep the things that they are instead of diving into the quantum, because in those particular problems quantum will not give you any advantage over classical. And then of course there is a set of problems that are not solvable either by classical or by quantum, but people are still working on this kind of problems. Those are known as the NP hard problems. Some of you from the background of computer science or mathematics might be aware of it. Anyways, so just to recap, what is classical? So the classical bit is something that the classical computers are basically working on. So classical bit, as you already know, has only two possible states, one and zero. So it is sort of like tossing a coin, and if you get a head, then you assume that the outcome to be the one, while if you get tail, you assume the outcome to be the zero, and from there you do your computation and so on. So that is the classical computation or classical bit, so to speak. Wherein in quantum, you do have these two states, like the zero and one, basically two particular states. You have two well defined states you have. However, the advantage in quantum that we can have is that the system can be in either zero or in one or in any linear combination of these two. So system can sometimes be here, 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 or sometimes be here, or sometimes be in the one state. Now one might ask why it is beneficial. So consider it like this. Consider a scenario where you are in a huge concert, and so concert is held, and let's say is held in some stadium, and there are so many people in the concert. Now the organizers basically wanted to make an announcement. So there are two ways those people can do an announcement. One is that they will go to the individual people, and they will go to the each and every people, and then they will make the announcement. So that obviously will take huge time. For example, let's say there are 50,000 people, then the organizer will go to the each and every people and make their announcement. So they need to make their announcement 50,000 times. Obviously that will take too much time. However, if the organizers can do the announcement over microphone system or over some system that is accessible to each and every participants, then in just one announcement they can share the information with each and every one. That is sort of like distinction between classical and quantum. It is not the exact analogy, it's a vague analogy, but again it helps in understanding the power quantum mechanics. So again, to rephrase, classical is 0 and 1. It is similar to going to each and every person and making an announcement. While in quantum, it is 0 and 1. But in addition to that, you can have any linear combination of these two. And not only that, whatever operation you are applying is simultaneously applied on each and every linear combination. So that is the advantage. Uh, so yeah, this position, this phenomenon is known as the quantum superposition, and it is denoted by this alpha 0 plus beta 1, where alpha and beta is some number. But yeah, if you don't understand any of this, don't worry. I'm just giving you a very basic idea of quantum mechanics, but as you explore it further, you will get to know more about this. I'm just giving you, for the sake of completeness, since we are exploring Qiskit, it is better to start with quantum. And this is how you represent a two qubit state. So as I said, so you have one qubit, you can represent up to two states. With two qubit, you can represent up to four state. Here also you see the quantum advantage, because if you have two classical bit, then you can represent four state, but in two qubit you can represent four states simultaneously. So that's the advantage. Then we come to the measurement theory. I will discuss this when I'm discussing the Qiskit, so it will be clear. Uh, it will be more clear when you do that. This is another phenomena of quantum entanglement, that is also something that you cannot find in classical setting. So quantum entanglement is basically when we have two particles that are connected in such a way that any disturbance to one particle is immediately seen onto the other particle, irrespective of the distance between these two. And so these two particles are then called the entangled particles. And yeah, this is the one important point, that people usually think of this phenomena to be violating the general theory of relativity, but it does not. And you will see that as you explore the topics of quantum teleportation or super dense coding, you will see that y does not violate the relativity. So one example of this kind of state is this phi plus Bell state. So you see the system is in superposition of 0, 0 plus 1, 1. And if you see that the first qubit is in zero state, then you immediately know that the second qubit has to be in the zero state, even if you are not measuring that, or even if you don't have access to that second qubit. Similarly, if you see that the first qubit is in one state, then you immediately know that the second qubit has to be in the one state. Again, it doesn't matter if you have access to that qubit or not, it will always be in state one. Then this is again another idea, another concept of quantum interference that is not available in classical theories. And the application of quantum interference is mainly used in the domain of quantum sensing and metrology. Okay, so now we come to the topic of our hand, that is the Qiskit. So this is how you represent a circuit in Qiskit. I will go through it each layer by layer. So you see this Q0. So this Q0 is nothing but your first qubit, or in Qiskit, the ordering is done from 0, 1, 2 onwards. So your first qubit is denoted as Q0, and your second qubit is denoted as Q1. So this is qubit 0, this is qubit 1, and this MEAS is nothing but your classical register. So now the idea of classical register comes. So what basically it means is that here you yeah, so here you see that your qubit can be in either state 0 or in state 1 or in any state in between them. So let's say if qubit is in this kind of a state, then it has certain probability that if you measure the qubit, then it will be in state 0 or in state 1. But when you measure the qubit, you need to use some classical register to save the value of that qubit that you have obtained. So to save the value of the qubit that we have obtained, we use classical registers. Yeah, and in Qiskit, so these qubits are known as the quantum registers, and in Qiskit, these classical registers are known as the classical registers. Uh, if you see this black wire, so this black wire represents the operations being performed on a particular qubit. So for example, this block represents one particular operation. Don't worry about it. If you don't understand what does this edge means, I'll explain it in a detail. So this edge basically means an particular operation that is being applied on the qubit 0. Similarly, yeah, you can ignore this dotted or dashed line. This just represents an operational difference. So what is happening is here you are applying quantum operations, and whatever you are doing after this dotted line are the measurements, and both are different, as we will see when I'll show you how to implement these things using Qiskit. But to basically distinguish between quantum operations and measurement, we typically use this barrier, or that is represented by these dotted lines. So yeah, as I was saying, this block represents a particular operation being applied on a qubit 0. This block represents a conditional operation being applied simultaneously on qubit 0 as well as on qubit 1. So what it does is it will apply a particular uh, rotation or a particular operation on qubit 1, given that certain conditions are followed here. I'll discuss this in detail as well, but just this is how the representation is used when we are dealing with conditional operations. And if you have multiple gates, then we always take time to be from left to right. It means that the leftmost gate is applied first, then the second leftmost gate is applied, and then the rightmost gate is applied. One thing is very important here is that the order of application of gates or an order of application of operators is very important. So you will have to go in a particular order. You cannot just say that, yeah, first I'll apply this operation, then I'll apply this operation. If you do that, then you will get something else. And these are some of the examples of the gates. I'll discuss that as well. So I think you all are already familiar with the blood sphere, and if not, then let me just say it very briefly. So blood sphere is something that we use to represent a state of a qubit on. So if, let's say, so this is my z-axis, this is my x-axis, and this is my y-axis. So if I consider my qubit to be in the state 0, then it will be over here. If I consider my qubit to be in the state 1, then it will be over here. You can have get 1 and get 0 over here. It is just there is nothing special about representing gate 1 over here and gate 0 over here. It is just done. It is a convention that people follow, and it has been followed by people, so we do that as well. But you can just as equally write 1 and 0 over here. It doesn't matter at all. So if you initialize your qubit in state 0, then the state of the qubit is represented by this blue line. You see that this is the state. If you flip the state, then you will see something like this. If you again, let's say, rotate your state along x-axis, or you apply edge gate, then you will see something like this. This I'm showing you just to show you that a particular operation, what is the effect of particular operation on a qubit represented in plot sphere. But if you are still confused in this, that is completely fine. You can just spend little time on this, and yeah, you will be able to understand it. But still, if you are unable to, you can always post your question in the Discord channel, and we'll be happy to help you out. Okay, so now let's directly dive into the quantum. So, Qiskit, so how does Qiskit work? So, let's say I'm the user. I will use Qiskit to write a particular circuit, write a particular code. Then I will use Qiskit runtime. So, that is like connecting my code to the cloud service of the Qiskit. Then it will do some intermediate state. We will go through this state, what are those, how they are done, and at the end it is implemented on quantum processor. So IBM has 7 or 8 quantum processor currently available via cloud, and in order to access that, you need to use Qiskit framework, and this is how you will do that. So again, you will write your program in Qiskit, then you will use Qiskit runtime to connect with IBM's cloud service, and then you can utilize the quantum processor to execute your program, and then this will again give you your output back to your local device. So, uh, as I said, Qiskit is an open source software development kit for working with quantum computers, and it is basically designed in very abstract format, so you can work with very simple gates, and then the rest of the thing is taken care by the Qiskit itself. At the same time, it does give you some access to modify certain things, and we'll see how one can do that. So these are some basic installation instructions. I'll share the slides with you as well, so you can go through it later on. So yeah, as I said, this is the simple pattern using which you can use your algorithm. So first you map your problem, you create a quantum circuit, then you basically transpile your circuit such that it is, uh, you know, transformed in such a language that it can be applied to quantum hardware. You execute, and once you have done the transpilation process, then you pass that transpilation to Qiskit runtime. This is basically an online cloud-based platform that will let you connect with IBM's hardware, and then it will give you back the result as well. So this is a basic pattern that you will be following throughout the Qiskit. Yeah, again, this is the same thing in some different ways where you will be, in order to, design your circuit, you will be using certain modules. So one of which is Qiskit circuit library. Then you will transpile. Then you will use primitives to execute, and I'll discuss that as well. And then you will use various visualization tools and certain modules from Qiskit to post-process your data. So Qiskit is divided into three modules, if you can say. So Qiskit not just lets you execute your quantum circuit or your quantum program into onto the cloud platform, but it also lets you simulate the same on your local. So you can do that using Qiskit module Qiskit Air, and from that you need to use Air Simulator, and these are the different simulation packages that you can use, different simulation methods rather that you can use. And using Qiskit IBM runtime, you can connect to actual quantum computers or quantum hardware. So this is a transpilation process. I'll not go into transpilation process now. I'll just directly go to the coding part, and we'll see from there. One second, let me share my screen again.
Until then, if you have any queries, guys, you can drop into Discord server where Q&A option is there. And we will open here also, but we will be seeing question from there only, Discord server. Yeah, Harsh, continue.
Okay, I hope you can see my screen again.
Yeah,
Is it
it's visible.
visible?
Yeah.
Perfect. So I'll be sharing this notebook with you as well. You can go through it. So I have given some basic, information for those who are not entirely familiar with quantum. So this part is where you will be connecting classical computation with quantum computation, and in this, I have not assumed any quantum knowledge whatsoever. So you can, go through it, and then we can always discuss on Discord. Okay, so let's design a quantum circuit. So how one will do that? I've already written code, but let me do that again. So first you will need to import the basic building blocks of the quantum circuit, that is quantum circuit itself, quantum register, and classical register. So to do that, let me import it from Qiskit. Yeah, I will import quantum circuit, quantum register, and classical register. Then I'll create a quantum circuit. Let's say, so once I have the quantum register, then I need to tell the Qiskit that how many qubits I need. So to do that, what I'll do is I'll name my quantum register, let's say, with qubits, and that will be quantum register, and I'll say, let's say, 2. So this will basically generate 2 qubits. Since I have 2 qubits, I'll also need 2 classical registers. So I'll just say bit equals to classical registers, and I'm having 2 bits. You can also give your, let's say, particular name. So if, let's say, I want to call it my qubits, I can do that. I can give any name whatsoever, and this will basically help in uh, addressing particular qubits. But for the example, I don't think we need to do that. Now, once I have two qubits and two classical bit, I can combine both of them to create one quantum circuit. So let's say I keep my quantum and I need to give a name to quantum circuit. So let's say, what could be the name? Let's say my circuit equals to quantum quantum circuit, and then I need to tell this quantum circuit which are the qubits and which are the classical bits. So I'll say qubits and classical bits. So the first argument will be what are the qubits, and the second argument would be what are the bits. So this is a very technical way to initialize any quantum circuit, but you can simply write this as well. Let's say QC, quantum circuit equals to quantum circuit, and I'll directly write 2 and 2. So this also is the same thing. Instead of explicitly defining qubits with quantum register, I can directly say that initialize 2 qubits and 2 classical bits. Both are completely fine, but for a moment, I'll just comment it out. Okay, now once I have created my quantum circuit, I need the first thing that I need to do is let's say print it in before applying any uh, quantum operations. Let me print it. So here I'm done the same thing. I've created the three circuits, and I'll just directly print the circuit, and you can see that I have Q0 initialized, Q1 initialized, and Q2 initialized, and three classical bits. The another good way of plotting will be this using matplotlib, and it will give you very nice visualization. So this is Q0, this is Q1, this is Q2. So I have initialized three qubits and three classical bits. Now I can apply any quantum operations that I want to do. So for example, let's say I want to apply, I think I've done that. Yeah, before quantum application, yeah, let's see the measurement part. So how that will go. So again, I'm initializing QC. QC is the name of my quantum circuit. This quantum circuit is initialized with three qubits, three classical bits, and then I'm directly measuring those classical bits. So I'm directly measuring those qubits, pardon me. So what I can do that is that see, this three is three qubits, and this three is three classical bits. So qubit is different object than classical bit. So whatever the value of qubit, I need to save it in the classical bit. So that is what I'm doing. So save 0th qubit's value into the 0th classical bit, save first qubit's value into the first classical bit, and save second qubit's value into the second classical bit. And if you see, and yeah, let me use MPL method here as well, and you see that the qubit 0 is being measured into the 0th classical bit, 1 is being measured into the first, and second is being measured into the second. So this is where you can define which classical bit to decode which qubit. You can interchange the order as well. If I, let's say, 2 0 1, it will work as well. So now the 0th is saved into the second classical, first is saved into the 0th classical, and second is saved into the first classical. And if you just want to do it straightforward, then you can do qc dot measure all, and it will do the measurement for you. Okay, so now once we have defined the measurement, now let's again go back to our circuit, and let's see if we can apply any quantum operations onto our qubits. So first to do that, what I'll do is qc dot x dot 0. So what this do is apply X operation or apply X gate or apply poly X gate on the 0th qubit of quantum circuit. So X gate applied on the 0th qubit of this quantum circuit. You can, and then print, and you see that X is being applied onto the Q0 while the Q1 and Q2 are unaffected. If I do the same thing for both, then instead of X, let me say Z this time, and I'll say 1, and here, okay, let me leave it as it is. So you see that Q0 on this Q0th qubit or the 0th qubit, X is being applied. On the first qubit, Z is being applied, while the Q2 is as it is. So this is how you address the qubit with the type of operation that you want to apply. Now, there are several type of operation that are available in Qiskit. So you can apply X gate, Z gate, basically any kind of gate that you wish to apply, any kind of quantum transformation that you wish to see, that can be done in Qiskit. And apart from this standard gates, X gate, Z gate, Qiskit also has a functionality to define your own gate and then apply that gate onto your circuit. So you can define custom gates and apply that on your circuit, and that will work just as fine. So you can do that as well, given that your gate is unitary. And if you don't know what the unitary gate or unitary matrix is, then you will again be exploring in the upcoming days. And yeah, again, if you have any questions, you can always drop into the Discord channel. Okay. So now what I have, okay. Yeah, before that, let me just show you what the rotations mean. So, we previously see the block sphere. Yeah. See this block sphere. So basically X gate or Y gate. So X gate is similar to what you have as NOT gate in classical world. So what NOT gate will do is it will turn any classical bit from 0 to 1 and 1 to 0, or vice versa basically. So similarly, NOT gate or X gate in quantum does the same thing. So if your state is in 0, if you apply X gate, it will turn into state 1. If your state is in state 1 and you apply X gate, it will again go to 0. So that is one-to-one correspondence between classical gates and quantum gates. And the same thing can be seen here as well. So if you see, the X gate will basically rotate your state with reference to the x-axis. So again, this is a block sphere. If you see, this is the z direction, x direction, y direction, and this arrow basically represents your state. So if your state, let's say initially it was here, so that will be in 0. So see, if your state is in 0 and now it is being slow, it is being rotated along the x-axis and it goes to state 1. So this is the effect of X gate. Similarly, there is another gate, or you already might have thought of that what if I do the rotation along y-axis? You can do that, and that will also rotate your gate from z, basically from 0 to 1. However, this rotation will add a phase factor to your state. So the 0 will turn into the negative iota into the 1. Basically, some phase factor will be there. But you don't need to worry about this. What I basically wanted to convey is that every gate is nothing but a particular rotation in a Bloch sphere. Now, this rotation can be in just one plane or along one axis, or it can be a complex rotation along all three axes. But every quantum operation, every quantum gate is nothing but a rotation in this Bloch sphere only. And one specific thing about quantum that makes it highly let's say approachable from classical, so to speak, is that each and every quantum gate is reversible. Unlike classical, you can reverse your gate and you will get the same state back. And if you dive a bit deeper into the subject, you will get to know the power of this reversibility. Again, and if you see the Z gate, then it will just rotate your state along the Z axis. So if your state was first pointed along the positive X axis, then it will just go to the negative X axis. Let me run this again, and you can see that it goes from here to here. Now there is another gate, as I told you that not every gate rotates along just one axis. There are certain gates that rotates along different axes at the same time. So H gate does exactly the same thing. It rotates both the axes X as well as along Y, and you will have this kind of transformation. Let me run that again, and you will see my state was here, now it has come to here. So for initially my state was pointing in Z direction. From there it has come to X direction. Let me run this again and focus on this particular arrow if you can. See this, from Z it comes to the X direction. So it is a bit complex rotation as compared to the previous rotations that we see. But again, as I said, each and every gate is just a rotation. Okay, perfect. Now we understand what the gates are. Then let us simulate one circuit. By simulation, what I mean is that instead of executing the circuit on the actual hardware, I'll just execute the circuit in my local. So for that, I'll import Air Simulator from Qiskit Air package, and I'll initialize by the name simulator. I run this, and then what I'll do is I'll sim.run. So this basically runs the experiment, and this basically gets the result of the experiment, and then we can visualize the counts. So before that, since we are running the quantum circuit, let me first define clearly my quantum circuit. Let me use this circuit, and I need to add measurement. Okay, so I have applied X on 0, Z on 1. Let me apply Y on 2, and then I'll also apply H. No, H. I'll apply later because H is a bit complicated. Measure all, and yes, so X is on 0, Z on 1, Y on 2, and I'm then measuring, and I have defined my circuit. Now I'll define again my simulator. I'll run the simulator, and this is what I got. So these are the counts that I've got, and if you want to see, then I'll use from Qiskit.visualization plot histogram and plot histogram. And I'll plot the counts, and you can see that for this particular combination of bits, I'm getting 1024. But if you want to really see something different, then what I'll do is I'll again go back to the single qubits, 1, 1. I'll comment out these things, and I'll apply H gate. So H gate will create superposition of 0 and 1. So the state will neither be in 0 nor be in 1, but it will be in the superposition of both. And you can see that H is being applied. This will create a superposition. Then I'm measuring. So half of the time I will measure the qubit in 0, half of the time I will measure qubit in 1. And let me execute the circuit, and if I print, you can see that half of the time you see 0, half of the time you see 1. And this extra bit you are seeing, that is because I have done the measure all. But if I do measure 0, 0, sorry, 0, 0, then you should not see that. Perfect. Okay, so if I, let's say, so what is happening here is I am first creating a 1 qubit, I'm applying Harderbad on it, I'm measuring it. That process I'm repeating 1024 times, because if you just do it once, you will either get 0 and you will either get 1. I guess it is good time to go back to the PPT. Measurement, yes. See, so Hadamard, what it will do, it will give us 50% of the time 1, 50% of the time 0. But if you just do it once, then it will either come into 0 or into 1. But you cannot say, you cannot predict it, because quantum theory is a probabilistic theory, and this is one of, again, the advantage. However, if you repeat this experiment, same experiment 1024 times, then you will see that almost half of the time you will find almost half of the time your qubit to be in the 0, and almost half of the time you will find your qubit to be in the 1. And this is what we are getting. So 520 times I'm getting my qubit in 0, and 504 times I'm getting my qubit in 1. If I repeat it, I might get some different number. And for that, I need to repeat the experiment and to see I'm getting a different number. This time 531 times it is measured in 0, while 493 times it is measured in 1. If I do it again, I'll see something else. 515 and 509. So this is the overall process of how you will execute your circuit. Now this I have done on air simulator only. So this I am simulating the circuit on my local, but you can just as well do it on the actual hardware. I'll quickly go through the process of doing that, because I think we are running out of time. So for that, you need to use Qiskit runtime service, and that you can use using Qiskit IBM runtime. You need to install this module separately from Qiskit, and from there you need to get an API key. So for that, you will go to the IBM Quantum Cloud platform, and from here you will get an API key and SCRN number. Once you have that, you post it here, then you will get access to the available hardware, uh, basically available hardware, freely available hardware. And these two machines, IBM Brisbane, so this is name of one quantum computer. The another quantum computer is named as IBM Torino. You have access to these two quantum computers, and you can just directly execute your circuit on this. But the process is almost similar. Just there is a one extra step of transvalidation involved in here. But I see that we are running out of time, so I will not go through the transvalidation process. However, you can, uh, you know, ping me on the Discord, and I'll explain you over there as well. Or Sumit, do I have time? Can I go through transvalidation process very quickly?
Yeah, sure, you can.
Okay, perfect. Okay, so I think we stopped our PPT here only. So let me continue from here. Okay, so now we just saw the example of applying Hadamard gate, X gate, Y gate, any rotation gate. But the IBM quantum computers will not be able to execute all the gates, and it executes only a certain number of gates. These are known as the basis gates. So this CZ and ECR, you can, these are the 2-qubit gates, conditional 2-qubit gates. So I'll show you one example. See, this is a 2-qubit conditional gate. Now, as I told you, it depends on the value of Q0, and well, it depends on the value of Q0, it will apply certain operations on Q1. So every quantum processor has this particular gate as its basis gate, and apart from there are certain gates. So you need to apply your Hadamard gate or whatever gates you applied in your qubit on your quantum circuit. You need to convert these gates in terms of this basis gates, and that is taken care by the transpilation process. So what you do is you see now all the gates. So this first 3 gates, that is constitutes to the Hadamard gate. So one Hadamard gate is now broken down into the 3 gates, and these 3 gates can directly then implemented on the actual quantum computer. And the C naught will remain the same, because hardware does support C naught gates. So this is where, if you are using the actual hardware, you need to do this. If you are using the simulator, local simulator, you don't need to do all these things because simulator can simulate every gate that you apply into it. But on hardware, you need to do this transpilation process, and there is a straightforward process. I'll include that into the code, and then I'll send it on the Discord channel so you can go through it. And yeah, so this is an actual quantum processing unit or quantum chip, you can say. So this is one qubit, this is second qubit, this is third qubit, this is fourth qubit, and all these things are the connectors. And you
But
see that
PPT
each.
PPT is not visible. I guess you haven't shared it. Still, we can see
Oh,
your notebook.
okay, okay, okay.
VS
Sorry,
Code. Yeah.
sorry, sorry. Yeah, my bad, my bad.
Attendance link is the same. And uh, Lakshita, can you share in the chat? And the code for today's cohort 37B.
Okay, is my slide visible now?
Yeah, it's visible. Yeah.
Okay, so as I was saying, every processor has every IBM quantum computer has a particular set of basis gate that is only applicable on to a state. So, as I said earlier, Hadamard gate cannot be applied onto the quantum processor. You need to convert it into in terms of this basis gate. So that is what being done here. You see that RZ, square root of X, and RZ. So these three gates represents one single Hadamard gates, and similarly other gates are converted in terms of RZ or sigma X, or basically the gates which are supported by your particular quantum processor. And each and every quantum processor has different hardware, different basis gate depending on the type of the processor. So Eagle processor and Heron processor. There is another Osprey kind of processor. So basis gate depends on the type of processor that you're using, and that is how you will do that. And so this is an actual quantum chip. So this is one qubit, this is second qubit, this is third qubit, this is fourth qubit. The order might not be the same as I told you, but yeah, these are the 1, 2, 3, 4 qubits. And these channels you see, these are the connections between the qubits through which C naught kind of a gate is being applied. And you see that each qubit is not connected to each and every other qubit. So that is why you need to use something called as the swap gate, but that is highly technical. So we don't need to go into that right now. And this is the actual qubit connectivity. So you see that qubit 1 is connected to 0 and 2 only, not with 15 or with 16 or with any other qubit. So if you want to connect these two, then you need to use something known as the swap. But again, the Qiskit is designed in such a way that it will take care of it by itself. You don't need to go into the all this process. You can if you wish to, but if you don't wish to, you can just simply write your circle, write your circuit, give it to transpilation. Transpilation will give you the circuit which is basically applicable, which is directly you can implement on the quantum processor. You do that and you will get your result back. It's as simple as that. This is again some layout and scheduling stage. I don't need to go into that. Lastly, I'll finish with what I started. Richard Feynman himself was the one who, suggested that we should use quantum computers, but at the same time, he was firm believer of the fact that nobody understands quantum mechanics. Thank you so much, guys.
Yeah. Thanks, Harsh, for the wonderful session. Hope people loved it. Lakshita, if you want to share your screen and share the code, then you can. Thank you for the applause, everyone. Yeah. So for today's cohort code, this session code is basically cohort 37B. You can just use the link which is shared in the chat.